So here I'm gonna give you some introduction about Riemann Stieltjes integral and maybe some its definition and some easy theorem about it. So let's step into the definition part. So define two functions f from ab to r and another phi ab to r, and let the gamma be partitions of ab, which is the parts where they define a and b. So the partition is gonna be from the points from A to B, the x0, x1, x2, xn, and xn, and choose a sample points where the ci is in between the xi minus 1 xi. We have an interval from A to B, and we have many points from x. Like for example, here's x0, x1, and some points here x2, x3 until xn, which our B. And then we choose a sample point ci in every single interval here and here. Like in the middle point, just a random one. We can choose this ci. Then now we can now define a Riemann Stieltjes sum as the following function, which is the multiplication between the f function of the simple on the sample points, and also the 5xi minus 5xi minus 1, and sum it together. Then we now define the Riemann Stieltjes integral as the limits of this thing, the limits of the sum, as the gap of the partitions goes to 0. What is my gap? Gap is the largest distance on the interval. For example, here we have an interval like this, from here to here, a small partition. So you can see like here is the smallest one. So the gap of these partitions from A to B is going to be this length. Okay, so as the gaps goes to 0, means like the cuts is getting smaller and smaller. Like the length of each gap is getting almost goes to 0. Yeah, that's a limit. Then as we're taking these limits, then we find the answer of the limits is the Riemann Stieltjes sum. Riemann Stieltjes integral. Yeah. Okay, so here we step into the first example. So consider the example this one is quite easy. It's for us to understand the definition, how it works, and try to make use on some simple questions. Right. Here we paste the definitions of the sum, the Riemann Stieltjes sum. Okay, so now let's get into it. So first of all, we already have two functions, so we have to define a partition. So this partition is gonna be from 1 to 3. So in this case, A is equal to 1 and B is equal to 3. So from 1 to 3, we define a partitions. Consider a partition. Then there always exists such xj such that xj is just larger than 2. Because here is from 1 to 3, so in the middle, maybe it's not the middle, but somewhere in between here must be have a xj such that it's just smaller than 2. Then the next one is gonna be like larger than 2. Then the xj plus 1 is larger than 2. It's just direct in the middle, or maybe larger equal. So we can write the xj phi here, xj xi minus 5xi minus 1 means the which is the behind term here, the behind term is gonna be 0. It's gonna be 0 whenever the I is smaller or equal to j. Because when it's smaller or equal to j, by the definition of this function, of these 5 functions, it is gonna be 0 all the way. So because when the I is smaller than j, then the xj is smaller than 2. Then we always get 0 for the xj even smaller. Yeah. For even like the terms even in front is gonna be smaller than 2, then smaller than 2 is equal to 0. Then for another case, for the phi xi minus 1 is gonna be equal to 0 for another case, for another direction, for I larger than j plus 1. Why is it? Because for larger than that, for example, the xj plus 1 is already larger than 2, larger equal to 2. So it is gonna be 1 on the 5, xj plus 1 is equal to 1. Okay, so when it goes larger and larger, it's both going to be 1 and minus up is equal to 0. Okay, so for both cases, it's going to be 0. So for the behind part, we can easily simplify the total sum into a simpler expression. So just write it. Only got one terms left, which is just the case where x is equal to j plus 1. So 5 xi minus 1 when I is equal to j plus 1. Just now I said the terms wrongly. So then we can rewrite this equal to fci. Then because 1 is larger than 2 and another one is smaller than 2, then it's going to be 1 minus 0. And this argument works for all partitions. So we can just say that for all partitions, it's going to be the same. Yeah, we can always find such interval, the xj and xj plus 1, that contain 2 and the point before 2. So as the gap goes smaller, as the gap gets getting smaller and smaller, the ci is chosen. So remember, the ci is exactly is chosen in between the cj. So the cj is chosen exactly in this interval. So we can say that as the gap getting closer, actually there are the range of you able to choose the points, right, is getting smaller, and you get getting closer to 2 as the gap of this getting smaller goes to 0. Then we can just write the integral as dy by definition is limit of gap goes to 0. Then this is equal to f2. Just here, we can just copy this thing into it as f2 and 1 minus 0. That's equal to log 2. So here is a simple theorem about the Riemann Stieltjes integral. So when the phi function is continuously differentiable, it means after it is differentiable, and after differentiable is still continuous. So after taking a derivative, then it's still continuous. Okay. Then this equality holds. Means we can just somehow visualizing is putting the phi into in front, then take a prime on it, then behind just replace by x. So how can we do this? We just do with MVT. We try to by mean value theorem. And by mean value theorem, we can say that exists a bi in xi to xi minus 1 such that the bi is equal to xi minus 5x xi minus 1 xi minus xi. Okay, so the statement of the mean value theorem is saying when the phi is differentiable, is continuously differentiable, then we can find a curve like that. For example, here and here is the a and b. We can just draw a line like that. Then we can, in the middle, we can always find a bi, which is the case bi here, a bi, and this bi having a tangent line is parallel to this. So it's its derivative is equal to the gradient from a to b. Okay, so we just apply it onto the interval of xi minus 1. Then we can get this. We can show that there always exists such bi. Consider partitions. We can always construct such bi in terms of a series that bi is in the elements of is in the interval of from xi minus 1 to xi. Then we just try to copy everything into it, here and here. Then we try to replace the behind parts with this mean value theorem, with the result of mean value theorem. We just try to move this over here, then replace up. See, you just notice that here and here, this part and this part is exactly the same. Then just can replace it directly. Then I can have bi, then another multiplication xi minus 1. As we take the Riemann Stieltjes integral, that means that we take the limit of gap goes to 0. So now we have to concern about the ci and bi. So ci and bi, because when back to our definition, we only have ci, right? The Riemann Stieltjes, the definition of Riemann Stieltjes integral. So now we have to prove like ci and bi is actually very similar, and yeah, very goes to very close to each other as the limit goes to 0. Yeah. So note that ci and bi is in the elements of xi minus 1 and xi. So as we're taking the gap of this, the partitions goes to 0, the interval is getting closer, because like xi minus 1 and xi is getting closer to each other. For the visualization, it's going to be like that, xi minus 1 to xi. Then maybe 2 points, maybe ci, bi, without loss of generality, just like put like that. Then as we squeeze it, as we have a like external, like taking a limit goes to 0, taking a limit of like the gap goes to 0, then you can see like it's also getting closer to each other. Then we can just write, with this reasoning, we can just write ci is equal to bi in some sense. Then as we're taking the limit of gap goes to 0, we just write this exactly the same thing, but the bi changed to ci. And bang, notice that is exactly the limit of gap goes to 0, and taking this as a function, then it's just like the multiplication, then it is the r gamma, okay, is equals to the Riemann Stieltjes integral of f phi prime, and here is dx. Because here you see that and one of the points is like, why is it dx? Is because here usually we take like the function phi, for example, I'll change the function name, psi xi and minus psi xi minus 1. And in this case, the psi is exactly equal to x. The psi x is exactly equal to x. So we just straight away write an x here. Okay? And here we prove our theorem. And let's step into an application on how do we use this theorem to make our life easier. Okay, consider this example. It's also a very easy one. So just for like easy understanding, consider the phi x. So let's, first of all, we need to use the theorem. We have to check the condition first. So the condition is saying they have to be, this phi function have to be continuously differentiable. So we try to differentiate. Prime x is equal to 1 over 4. It's obviously continuous function. It's just a constant function. Then we can try to use the theorem. As we're taking the limit from 0 to 1, f is equal to e to the power of x. Try to write it more vigorously. Is equal to 0, 1 f phi prime dx is equal to, taking the integral from 0 to 1, e to the power of x, and this after taking the derivative of phi function is going to be 1 over 4 dx, and it's very elementary function, then we can have the 1 over 4 outside, ex, then 1 and 0 over here. We just sub into it. 1 over 4 e minus 1 over 4 e to the power of 0 is equal to 1 over 4 e minus 1. Okay, that's the answer. And that's all for me on this topic. Very, very introductory proof and like some definitions, also like an easy theorem about Riemann Stieltjes integral. Hope this helped you to understand more about this theorem. Thank you very much.